Welcome to our presentation evaluating the prospectivity of the Sleipner field system. So to begin, the Sleipner field is located on the eastern section of the South Viking Graben in sector 15-9 of the Norwegian North Sea. Its main fields are Sleipner West, Sleipner Ost and Volv, located primarily within block 15-9 of the Norwegian sector. The north-south trending block is characterized by normal faults formed during the early stages of the North Atlantic Rift system, and it's located in the lower Jurassic Hugin, with its formation primarily being composed of sandstones, shales, and siltstones. The field is an example of a complex geological environment with significant resources from its rich geological history, including black oil and natural gas. Figure 1 here is an image showing a geoseismic cross-section of the South Viking Graben. Natural gas can be seen in the Triassic, Jurassic, and Paleocene sands within the Sleipner region, with black oil also present in the Sleipner West and the Volv structure. The Sleipner field is a good carbon reservoir. It's been used for carbon capture storage since 1996, with the Utsira Formation being its primary carbon storage reservoir. Geological history shows that there were no large tectonic events following the deposition of the Utsira Formation, suggesting that the Sleipner field is tectonically stable and suitable for carbon dioxide storage. Further research projects have shown that seismic surveying can be used to monitor injected carbon within the geological storage reservoir, and research has shown that the most suitable rocks for carbon storage are generally porous, impermeable sandstone formations for capture, overlain by impermeable clay caprock formations. This is effective for storage as it prevents its migration. The Utsira Formation is also overlain by the Hugin Clay Formation, which acts as a caprock for any of this migration that may happen. And the sandstone layers in the Utsira Formation have good porous and permeability properties, as its mudstone layers can act as barriers to prevent carbon dioxide from escaping. The Sleipner Carbon Injection Project was the world's first industrial offshore carbon capture and storage project beginning in 1996. This injection project began with a planned continuation for 2 more decades at a rate of approximately 1 million tonnes of carbon dioxide per year. The injection point for this project is close to the base of the Utsira sand, around 200 metres below the reservoir top, through a near horizontal well. This well is 1,010 to 1,013 metres below sea level, with the injection occurring through a 38-metre long perforation. Figure 3 here shows the Sleipner being situated towards the southern limit of the Utsira sand, where its sand reservoir is around 200 to 300 metres deep and 100 to 800 metres deep. The Utsira Sand Formation is a large and deep saline sedimentary aquifer around 26,000 kilometers squared. The sand forms part of the Myo-Pliocene Utsira Formation, situated within thick post-rift succession of the Northern Sea Basin. The saline water from the formation can also be used for water injection in deeper reservoirs. As part of the Sleipner Carbon Injection Project, carbon dioxide separated from natural gas produced at the site has been injected into this large sand reservoir since 1996. The injection of carbon dioxide into the Sleipner reservoir is significant, as it represents one of the first large-scale applications of carbon capture storage technology.
This section handles about the source rock. First, all of the formations that could be source rocks in the Sleipner field were formed in the Jurassic, and depending on the type of kerosene, it is divided into oil-dominant and gas-dominant source. Kerosene is known as a source material of petroleum, and it is classified into 3 types according to the difference between hydrogen to carbon ratio and oxygen to carbon ratio. Dropen and heather formation are type 2 kerosene and silty claystone, which has high gamma ray. It forms primarily in the open marine environment and tend to produce oil, whereas Sleipner and Hugin formation are type 3 kerosene, and it composed with sandstone, which shows low gamma ray. It has a low hydrogen to carbon ratio and high oxygen to carbon ratio. It is mainly derived from the terrestrial plants and has low oil producing ability. However, when organic matter is matured, a large amount of hydrocarbon gas is produced. Slipner and Hugin Formation, located below the Dendropen and Heather Formation stratigraphically, and it represents a transgression of this field, changing from terrestrial to marine environment. When you look at the figure 5, hydrocarbon was emplaced into the Sleipner vest from the south and subsequently migrated to the east, and it fills oil into the green-colored Voe field and gas condensate into the yellow-colored Sleipner oat field and spills out. And this migration occurred between 70 and 45 million years ago. The hydrocarbon gases in Sleipner vest are thought to represent a mixture of gases generated from primary cracking of kerosene with gases that are derived from the thermal cracking of oil. In figure 6, because the oil-prone source is above the gas-prone source, oil-prone source rock can capture the natural gas which is originated from the shore face sandstone of the Hugin Formation in the Sleipner vest. In other words, more dense claystone such as Upper Dropen and Heather Formation can seal natural gas. As I mentioned earlier, we can see in figure 6 that gas condensate was captured by gas-prone source in Sleipner oat field, and oil was captured by oil-prone source in Voe field.
Okay, so it's important to note that in the Sleipner field area there has been lots of extensional faulting, especially within the Jurassic period. And we can see this in these north to south, northwest to southeast trending lineaments, which actually do move across another fault between the Sleipner Terrace and the Gamma High area. Now, these north to south, northwest to southeast trending slopes have suffered repeated strike-slip offset, especially once again during the Jurassic period. And in the southmost lineament, we actually do see that south of it there is no gas or condensate whatsoever, and that's due to limited or even no closure to the south of the fault, whilst to the north of the fault there is full closure at the faults, so the reservoirs have been sealed. Now, at the current time, there is not much gas condensate left within the area, but these could still possibly be used for CO2 storage. Now, if we look at the figure on the right, we see that we see a figure relating to the injection of CO2 within the Utsira formation, and it's actually spread into compartments, and these are due to interformational shale, which is only 1 to 2 meters thick, with the exception of the topmost shale, which is about 6 to 7 meters thick. And as we can see, there's been migration of several hundred meters, or a couple hundred meters. So this should all be taken into account for future CO2 storage endeavors. Now, once again, because northwest to southeast, the area is on a gentle slope gradient upwards. For future storage, we should expect migration to follow the same path. And we can see in the top left, the trap system has actually been highlighted. So there shouldn't be any spilling, provided that we respect the amount of the volume of the traps. So this is an image taken from a seismic reflectivity survey around borehole 15-9-13. And as you see, as I mentioned before, there are lots of examples of rifting and extensional faulting, and in general just fault activity in the area. And those have been outlined with these black lines along the sides. And we can see that there are many areas of high reflectivity where we're expecting thicker or denser layers, and then immediately followed by far less dense layers, which are indicative of effective traps and good seals, as well as below all these, once again quite thick quite thick strata, quite dense strata, which is a good indication that there shouldn't be too much lateral migration in the future.
So on this slide, I'm going to be talking to you a bit about the seal. And as you can see, the well logs from the study area show that there's thin beds of mudstone that can be seen within the sand reservoir unit, which is shown on the bottom image by the high gamma ray peaks within the sand unit. These units typically range from about less than a meter to just over 2 meters in thickness. However, they are not laterally consistent. The bottom image also shows a thick 5-meter mudstone unit that can be correlated between the different logs that separates the uppermost sand unit from the main reservoir sand beneath. Although these reservoir units are usually typically made up of around 70% sand, these mudstone layers within the reservoir serve as large permeability barriers and have been shown to have a big impact on how much CO2 is trapped inside the reservoir and how it gets moved around inside of it. This can be illustrated in the top reservoir image, showing mudstones of various thickness overlying layers of CO2 saturated sands, with the mudstone units helping trap the CO2 between each of the layers. The sand unit is then overlain by the Norland Formation, which is a 50 to 100 meter thick mudstone unit which forms the reservoir caprock. The principal reservoir caprock is a basin-restricted mudstone that extends more than 50 kilometers west and 40 kilometers east of the area which the CO2 is injected, so far beyond the plume estimated final migration footprint. So on this slide, I'm going to be talking a bit about how well this seal traps the CO2 beneath. So the top diagram shows the CO2 plume imaged as a number of bright subhorizontal reflections within the reservoir, which can be seen to be growing with time. It also shows how the layers of CO2 are trapped beneath both the reservoir mudstones and then also this reservoir caprock at the top. The bottom diagram shows the development of the upper plume within the topmost reservoir layer, showing that it's increased with time. However, it still remains trapped underneath this caprock. This low saturation CO2 is most likely the result of upward percolation through the mudstone beds, which are semi-impermeable. However, migration through the caprock seal is considered to be very unlikely given the high capillary entry pressures of the water-saturated caprock, the lack of significant faulting, the porosity values, the permeability values, and all of this suggests there's been no evidence of leakages, and that makes the mudstone an excellent seal.
Alright, so how valuable is the Sleipner field for us? Now, as we've seen, there are many good examples of good reservoir rocks and good traps and the seals in the area. Although being of relatively high porosity between 30 and 40% or 30 to mid 30%, we still have good opportunities for carbon storage. And obviously, even though there are high porosities within the seals, we can still expect there to be mineral trapping as time goes on, due to obviously CO2 being mineralized within the capstone, and of course being trapped underneath the capstone as well. So, many of the strata also within the area are quite carbonaceous, and in reservoirs and in the reservoir rocks, this is actually quite useful because it means that they are water wet and useful for water injection. So whatever oil or gas condensate is left within the strata, they are suitable for enhanced oil recovery, and in the future would also be useful for storing carbon dioxide. And yeah, this is the evaluation of the prospectivity of the Sleipner field area, focusing on block 15-9. It shows a lot of promise due to large reservoirs and not too much lateral migration, although we can expect to see a few hundred meters, especially in the higher up strata, of vertical migration.